Example number 2. So same directions. Let's go to work. First step is to determine the first partial with respect to x. So that's going to be 2x. That's going to be 0, minus 2, and then 0, 0. Next, let's determine the first partial with respect to y. So that's going to be 0, negative 2y, 0, plus 2, and then 0. All right, so what we're doing now is we are creating a system of equations based on these two first partial derivatives. So we set each one of them equal to 0, and then we solve the system. Now, again, this is another situation where this system should be a piece of cake because each equation only consists of one variable. So you just solve these things as two separate entities. So in the first one, what would x be to make this a true statement? It would be 1. In the second one, what would y be? If you solve for y here, what would y be equal to? 1. All right, so what does that tell us? You have a critical point where at this x comma y input value, this point, 1, 1, okay? So f of 1, 1, whatever that ends up being, that's going to either be our relative min, relative max, or a saddle point if our second partials test is conclusive. Now, I'm going to tell you right now, every one of the problems you're going to possibly have, the second partials test will be conclusive. You will get an answer generated. All right, so with that being said, let's go ahead and look at the second partial with respect to x. That's going to be the derivative of this, which is 2x. And now the second partial with respect to y, based on this, the derivative of this with respect to y would be negative 2. Wait a second, this isn't negative. This isn't 2x. Jeez. Unbelievable I made that mistake. It's just 2. Okay, moving on. Let's look at the second partials with respect to y now. First, based on the first partial with respect to x. So now you look at this, derive it with respect to y, and you just get 0. Okay? All right, so remember our what? Remember our second partials test. Okay? So this is what it actually looks like. I'll go ahead and write the whole thing out now as it appears on the paper. So even though these are constants, I'll show you what's happening, okay? So the discriminant would be equal to what? It would be equal to the second partial of your critical point, which is 1, 1, okay? So your a and b would be, your a is 1, your b is also 1 in this case, times the second partial with respect to y of 1, 1, minus what? Minus the first partial with respect to x, second partial with respect to y of the point 1, 1. This is our critical point. That whole thing squared, all right? But like I showed you in example number 1, what's happening here? Well, in every one of our second partials cases, you only have a constant. This is not always going to be true, but it definitely is true now, okay? So what this is going to generate is 2. This whole thing right there equals 2. This one is equal to negative 2. This whole thing right here generates negative 2. All right, minus what? Whatever this would generate, which is, again, another constant, 0, and then we square it. Of course, it's going to be 0. Okay, now in this case, we end up getting what? We end up getting a discriminant value of negative 4, which is less than 0. Oh, so because it's less than 0, because this value, our discriminant, the value of our second partials test, because it was 0, less than 0, then you're going to end up with a saddle point. All right, saddle up and ride. So let's see what happens then. What happens is you write down the answer. Therefore, f of 1, 1 equals what? Is a saddle point. Well, what is the actual z value? What is the actual result of f of 1, 1? How do you come up with it? Oh, you plug it in. So we get 1 squared, 1, minus 1 squared, 1, minus 2 plus 3. That's 1 minus 1, that's 0. Minus 2, that's negative 2. Negative 2 plus 2 is 0. 0 plus 3 is 3. So it's actually an ordered triple, 1, 1, 3, giving us at that point what is called a saddle point.